Hi girls, so here's a presentation on improving the DC motor. It's on our sites page. If you were to click on the link, it'll take you to the presentation. You'd also see next to the link there's a worksheet, and I'd like you to open that up and complete the worksheet as you go along with the presentation. So let's go through this presentation. So we know in a simple DC motor that it acts like this, but as you saw today, they don't work as well as you'd like them to in real life when you have this orientation of the bar magnet. As we've learned, so with that sort of DC motor, this is the sort of torque that you would get, okay? You have a maximum, it goes to a minimum and maximum, minimum. So for every half a turn, that's half a turn, and then that would be one whole turn. Okay, so this is done one and 3/4 of a turn, that this particular motor that I've got here graphed on this graph of torque versus time. And how do we make it more powerful or more efficient? Well, as you saw, one way to make it more powerful or more efficient is to have a radial magnetic field. So with the radial magnetic field, it allows for the angle between the plane of the coil and the external magnetic field to be close to 0 degrees, allowing for a more consistent torque. So when we're looking at the torque equation for motors, this is the equation that we're looking at. Where is it? Torque equals NBIA cos theta. Torque on a motor. Let's go back, see if I can find the equation. HSC. Here we go. Torque equals NBIA cos theta. When we're thinking about that equation, what we're saying is that the theta for the torque equals NBIA cos theta is largest. Okay, the angle's actually not there. Let's see if we can find a better one. No. Here we go. Oh, they got cos Q. Let's just say it's theta. So torque equals NBIA cos theta. So this becomes larger. So the torque isn't larger, it's just at a maximum for longer. And as a result of the radial magnetic field, the coil will also rotate faster. So what I'd like you to do to complete this worksheet is you take a screenshot of this picture, okay? Take also a screenshot of the graph and use those screenshots to complete the worksheet. So radial magnetic field, you insert the image of the screenshot, insert the image, explanation of how it improves the efficiency or increases torque. So you'd write that in here, okay? Allows for plane of coil to be parallel to magnetic field for longer, therefore allowing maximum torque for longer. This also means the coil will rotate faster. All right, and then lastly, insert your image. Here's the image of the change in torque as a result of the improvement. Okay, and you do this in a similar way for each of the improvements that we're going to come across. Okay, so it would have be at a maximum torque for longer. For this reason, it would also rotate a little bit faster. It would have the same maximum torque. All right, you can also add more coils. Notice here we've got 2 coils. And why is that the case? Why does it increase the torque? Well, torque equals NBIA cos theta. So you've got, if I have 2 coils, it means the torque is twice as large. Okay, so doubling the torque Doubling the number of coils will double the torque. I'd like you to do a graph for that one. I don't have a graph for that, but if I did have this sort of graph, then the torque would be twice as large. If I had 2 coils, if I had 3 coils, it'd be 3 times as large. Okay. All right. What I could also do is add another coil at 90 degrees to the other coil. So here I've got one coil attached to one split in the split ring commutator, and then I've got another coil that's perpendicular at 90 degrees to that initial coil. And so what I've got is 2 splits here. And what would the torque look like for a motor like this? Pause now and see if you can't draw it. Give it a go, see what you think. Alright, well let's see what it looks like. So I've got this, get rid of that. What would it look like? Well, each side of the coil would experience a torque that looks like I've got one coil experiences a torque, the one in green, and the other side of the coil experiences a torque, that in blue. Because they're attached to the one rotating system, we'd add their amplitudes. So here I've added the amplitudes, and then finally I've erased it, and this is what the torque would be. So this would definitely make the coil, the torque more powerful, okay? A larger torque if we've got 2 coils. Yeah, 2 coils in this case. So 2 sets of coils 90 degrees apart with 2 splits in the split ring commutator. What about if we had 3 sets of coils 60 degrees apart? How many splits would we have for that split ring commutator? You can see we've got 1 set of coils, 2 set of coils, 3 set of coils. Don't worry about this iron bit here. We're going to go through that in a moment. See, this is the coils are wrapped around what we call a soft iron core. Don't worry about that. But if we've got 2 sets of coils 90 degrees apart with 2 splits, then we're going to have we're going to have 3 splits that are going to be 60 degrees up. We're going to have 3 splits 60 degrees apart in the case of having 3 sets of coils. So that's another improvement, having more than 1 coil. But like I said here, what about the soft iron core? These coils are wrapped around what we call a soft iron core. And why is this needed? Well, first we need to know a little bit about iron. Iron is a magnetic material, meaning that if I had a piece of iron, inside the piece of iron it's got all of these little domains that point here. They're represented by this little arrow, which points in the direction of where the north is. The domains are all randomly aligned. But when I wrap some current carrying conductor around a piece of iron, I can get all of those domains to line up. And when I do that, it intensifies the magnetic field. So if I've got a current carrying conductor here, lots and lots of loops wound around a soft iron core, essentially what I'm doing is I'm lining up all the little domains in this piece of iron, and I'm creating a much stronger electromagnet, which if I place this whole system in the presence of an external magnetic field, the field that is created by the current carrying conductors will interact with the external magnetic field a lot larger, and I'll get a much larger torque. So wrapping a coil around iron core, it intensifies the magnetic field created by the current carrying conductors, therefore increasing the interaction of this field with the external magnetic field, thus creating a much larger torque. Or in other words, wrapping the coil around an iron core makes the torque larger. What else? I haven't asked you a question. What else could provide the external magnetic field? We've been providing it with a permanent magnet. What else could you use to provide the external magnetic field? Have a think. If you said use an electromagnet, then you'd be right. What I've got here is I've got current carrying conductors that are designed in such a way that if the current flows through them, we can create a magnetic field here from left to right. So rather than having the north here and a south here, I've got current carrying conductors creating the magnetic field into which I'd place a set of coils like this that would go right in the middle, and I would get those coils rotating. And the question is, what would be the benefits of using an electromagnet rather than a permanent magnet? Well, the benefits would be that if I increase the current flowing through the current carrying conductors, I'd increase the magnetic field strength inside. And this would increase the torque because it would increase the size of B for the torque equation. So I could easily increase the size of the magnetic field strength by using
it's the last 5 minutes of the coin line.
by using an electromagnet. Okay. Also, I could turn my motor off. I could get it stop rotating simply by turning off the current that flows through these current carrying wires. If I turn the current off, these magnetic field lines wouldn't exist and the coil would stop rotating. So, can increase the size of the external magnetic field by increasing the flow of current through the electromagnet. This would increase the size of the interaction between the external magnetic field and the magnetic field produced by the rotor coil. As such, the torque on the coil would be larger. So they're the improvements that can be made to a DC motor. We're going to look at some of the limitations of a DC motor a little bit later on, but what I'd like you to do is complete that worksheet, and then I'd like you to open up the presentation and watch this video and take some notes if you want. This is how a real DC motor works. It's a fantastic video and I'd like you to watch it. Alright, thanks girls.